And then I'm going to add it, and then we're going to work with it. Now, another thing that you may see from the moment is that I have changed the style, okay, for the syntax highlighting. It is much whiter. Yesterday I was looking at the video in YouTube, and it had very little contrast, in my opinion. So on the plus side, I think this one has much better contrast. On the negative side, this is not a semantic highlighter, meaning that we're going to lose things like a different color when calling functions. Sorry about that. This is still a work in progress, trying to find the better way to express the code. All right, so here we have this mock encoder. This is a fixed size byte oriented encoder for the compressor. Now, one important thing is that we are not going to need a definition for symbols, because we are not storing them into a vector of symbols. And the way we're going to calculate these four numbers depends actually on less parameters. So many less that we're not going to use an encoder config. Instead, we're going to put all those parameters here. In fact, they're going to be bytes for length, and bytes for distance. Another important thing is that, yes, the writer is no longer this type of writer. We need to write into a file. And I said this, I think, last week. Just give me a second. The idea is that, yes, that we can write not to a file, but directly to any implementation of the write thread. So this should be a mutable reference to an implementer of write. And now the configuration simply becomes bytes for length and bytes for distance. And yes, with these two numbers, we're going to calculate all the rest. So bytes for length, bytes for distance, and yes, of course, we need to receive a return to this. Something that implements, right? the right trait. We can't do this anymore. I think that actually even in the other, I think that we can remove this. So now, as you can see, the issue is that the reference here, okay, no, sorry, this, this, is that this is going to create a problem for us, but the problem time. So now it looks like it's fine, but it is not. But at the moment, we're going to keep it like that because we're still doing some shenanigans here. We are going to have a problem here with the ownership of the writer. We'll see. But yes, here we have it. So now the thing is that at the moment, we're going to make things simple and assume that we can work with the writer. You are receiving a mutable reference, so we don't receive the full ownership. I think that's how it works. So we don't need to write the results. It just works. So now let's start calculating these little functions. Maximum length for literals and references, right? So that obviously depends on bytes for length, right? If the data is written as unsigned integers, then obviously the idea would be that the maximum reference length would be 1 to 8 times, because it goes by bits, not bytes, bytes for length. All right, but this has a problem. This doesn't take into account that we also need to encode 1 bit to say if the symbol is either a reference or a literal block. And because distances only occur for references, it makes sense that that flag lives alongside lengths. Okay, meaning that we should need to deduce 1. All right. Sorry. We need to reduce 1 to the number of bits of the shift. And is that correct? Is it actually the number, or so then the maximum length? No, right? You may think a number that lives in 8 times bytes for length minus 1 has a minimum value of 0, a maximum value of this minus 1. That is true. But that would allow us to encode a minimum number of 0. But here's the thing. We are never going to encode a reference with a length of 0, right? Because get break-even length is actually the minimum length of a reference that is going to consider to be valid. So actually, what we need to deduce here is the get break length. Okay, this is actually, sorry, not minus. It's a plus, meaning that the 0 is encoded, is actually encoding self get break-even length, and this minus 1 encodes actually the maximum. Okay, let me show you. The thing is that if I want to codify reference length, what does it take? Well, as I said before, that row length has to be at least get break even, right? I'm going to flip around the query. And also row length has to be smaller or equal than the maximum length reference. Okay, that has to be true always by default, no matter what. Okay, we are not going to allow something to be encoded if it's not the minimum and not if it's beyond the maximum. And the idea is that the encoded reference is the row length minus break-even length. So the break-even length gets encoded into a 0. So what is the largest number that we can codify like this? Obviously, is this, meaning that set get max length reference. Okay, which would be this number in the edge case, minus this. This should be equal to what we can encode in this amount of bits, which is 1 size 8 times 7 bytes for length plus 1 minus 1. Okay, these two things have to be the same. So obviously this is an equation, and if we just want to calculate this number, we just need to move this to the second side. So obviously this has a minus, needs to move to the second part with a plus. All right, so what do we have? One inside minus one plus, oh, let's put the minus one here for clarification, and this. All right, so we know how to do some basic maths here. So this implements the maximum length reference. Now, what about the break-even length? I think that we had documented that in the code tray. Is the minimum reference length that encodes in less bytes than length literal bytes. So here is the idea behind the break-even. Imagine that I have much of this break-even length, let's say length 3 or length 4, right? And that means that we need to write length plus distance, so length bytes, so bytes for length, sorry, bytes for length plus bytes for distance, bytes in total. Or we could just write bytes for length plus 4 literal bytes. Right? So in which case does it make sense to encode this as a reference instead of literal bytes? So we may think, oh, it just depends on bytes for distance being less than 4, right? Or basically get break-even length is just equal to bytes for distance. As soon as bytes for distance, as the match has a length equal to bytes for distance, then encoding it as a match takes exactly the same amount of bytes as encoding as a literal. Yeah, but what if a literal block is already underway? Right? And yes, this is something that can be done afterwards in terms of optimization, is that get break-even length can be variable depending on whether or not the compressor is accumulating. But the thing is that if a literal block is already underway, this match of 4 only takes 4 literal bytes added to a literal block that is already underway. So in that case, the match, so the gate, the break-even length happens not when the match has byte for distance length, but when it has bytes for length plus bytes for distance. Sorry, when bytes for length and bytes for distance, if it's the same, right? If that takes 4 bytes, it actually takes the same amount. So it would be in reality byte for length plus byte for distance plus 1. Okay, so best case scenario for a match, this is equal to bytes for distance plus 1. Because obviously, when bytes for distance is the same as the length of the literal bytes, we are breaking even. It takes the same amount of bytes, but encoding it as literal means that if we have a little block underway, it encodes in less and give us the opportunity to try for a match on the remaining bytes of this match. Okay, we got a match on the first byte of length 4, but what if on the second byte I get a match of 4 or 5, etc.? Right, so best case scenario, it would be this. Worst case scenario, which again, it is when there is a literal block underway, it should be bytes for length plus bytes for distance plus 1. Because once again, if it's the same, encoding it as literal block make more sense. Now, I don't think it is a good idea to use the worst case scenario, because that only allows to have very, very long matches, and maybe shorter matches can be encoded more efficiently in the next step, right? In the entropy coding phase. So I think that we're going to go for the best case scenario, meaning that this is going to be bytes for distance plus 1. All right, so now we have these two functions dealing with the reference length already figured out. What about the distance reference? Here it is more simple. We're never going to have a distance of 0, because distance 0 is now cannot match itself. So the minimum value has to be 1. And obviously, that means that we have something. So if we take this basic equation, okay, of about what it is possible in this amount of bits, and then adding the minimum, the floor, now the floor for distance is 1 all the time. So as you can see, you can remove this, and that is the maximum distance reference, meaning obviously that when we want to codify a reference distance, the raw distance has to be at least once, and maximum the max distance reference. Removing the floor, which is 1. Okay, so you can see that all things tend to match. So now we know how to codify a reference length. and that depends on the boundaries of break-even length and max length reference. We know how to codify a reference distance, which is bounded by 1 and max distance reference. What about the maximum length for a literal? Because we could assume. So we're not going to, so we start with the basic equation, right? Obviously, so we have still, here we turn it to remove 1 bit. Sorry, let's come back to this. For literal blocks, right, that needs to be encoded also in length. The floor in theory is 1, right? We're never going to have an empty block. But here's the thing. How do we encode an end of file symbol? Because an end of file symbol is neither a reference or a literal block. There's something that we did in Velociterra, and I think it is a good idea, is that when the encoder is configured to use end of file, the end of file symbol is encoded like a literal block of length 0. And that means that we do have a floor, right? If we say no, the floor is 1 by default, so we're going to add the floor here. What if the floor is not 1? What if the floor is 0? Because we want to encode EOF. Okay, so the idea is that floor is equal to if self means EOF, then the floor is 0, because we're going to encode the 0 as the end of file symbol. And if we don't, then just the minimum length is 1, so we can push the maximum literal length by 1. Right, so we could do this. However, there is a trick in Rust. Is that in Rust, a Boolean value as any integer value, like any size, is equivalent to if Boolean value 1 else 0. This is important because this is not how C works. In C, or at least back in the day, because I stopped in C 95, I think that was the number of the name of the standard back in the day. But in C 95, there were not real Booleans. C++ was having Booleans, but I think they also did the same trick, that they encoded the true value to -1, not to 1. But in Rust, and this is important, in Rust, they are encoded like this. And as you can see, these are the opposite values than what we need. So obviously, the only thing that we need to do is to negate. And with this negation, this just becomes this. These two are equivalent. All right, I think it's a great trick from Rust. So now that means that if we want to write a codified reference length, sorry, codified literal length, we can calculate floor again, and then floor would be the row length, and the row length on the length of literal. Except that, remember, this is not how it works, because when we need EOF, we still want to reserve distance 0, specifically for the end of file symbol, not for a distance, so not for a literal length. So the literal length still starts at 1. The only difference is that, like here, we do need to remove the floor, right? So when we need EOF, let me think about it. When we need EOF, this becomes a 0, and we don't remove anything, so a row length of 1 still is a 1. Perfect. When we don't need an EOF, so this is false, this is true, floor becomes 1, and we remove 1, so the minimum length is encoded into a 0. Correct. Now, one thing that we can do, because we are calculating this all the time, and this doesn't change because this depends on its EOF, is to actually make floor literal floor a private attribute, so it doesn't need to be recalculated all the time. We already have it there. So remember, this is not in COF exercise. What happens? Oh, the comma. The literal length. Oh, thank you. Right. So now we don't need to calculate the floor. So we have it already. Same here. So basically, a length for references is between break-even length, maximum length. For literals, is between 1 and max length literal, with the caveat that the actual floor depends on whether or not we need COF, etc., etc., etc. So that we can actually codify EOF as a literal length of 0. But yeah, now we have all these 4 methods up running. Let's write a DOF. So we're going to start with the same. We're going to keep the debug assertion. Different now is that instead of writing a push, we need to write what? And right there. So another thing that we can do is, because now this is fixed size, we can actually own an internal greeting buffer. Okay, so we can use an internal buffer to write all of that. And the size of this slice is going to be bytes for length plus bytes for distance. Now, the issue here is that this is a reference. We don't own it. So if we box it, we own it. So if internal buffer is a box of U8, sorry, 0 U8, and the size is bytes for length plus bytes for distance. I doubt it is correct, by the way. I'm just in a constant. Okay. So how can we do this? We can create a vector. Then we extend. Now remember that is a way to make the vector to have a single byte repeated all the time. And at the end, we just do this in 2 box slice. Right? But before that, again, we need to extend not from a slice, but by, it was something like resize. So show me the help. Yes, resize or resize with. So resize with a function, and resize just the pure resize. Oops. Resize, you say what is the size that the vector should have, which is bytes for length plus bytes for distance. And we can initialize it with whatever we want, which is just a 0. So the size is again bytes for length plus bytes for distance. What's the problem now? Oh, our method into box size is available on immutable like of integer, so okay. So the resize doesn't resolve the continuation. So we need to make more inputs like new v resize v into boxes. Cool. So now here in internal buffer, we have a slice. So the box obviously, but we have a slice. Of fixed line. So now in order to write EOF, so what we need to do is self internal buffer 0 equal to first the flag. Remember, the first byte is the flag that we're going to use for this is a literal block, and I'm going to say that the flag is bit set. All right, and then for x in 1 to 7 bytes for length, except the first one, self-internal buffer of this to be 0. Okay, so we are encoding the EOF symbol as a 0, but there is 1 bit set, so it is taking like if it was length for a literal block. And now we write the slice, but from 0 2 bytes for length. And where's the problem? Oh, yeah. This. All right. So as you can see, writing EOF is not so hard. You can also assume that writing the rest is also going to be kind of easy. Maybe yes, maybe not. Basically, we need to convert a number and use size to be more precise into a sequence of bytes. There are a few ways to do that. I think I'm going to do it with a direct transformation to what is called big endian / little endian representation, because it already provides those bytes. The other is how to copy those bytes into this internal buffer, because those functions, so transforms into big endian, little endian, they don't work with variable size slices. The slices are equal to the number of bytes that are needed. So if a use size takes 8 bytes, then it's going to put whatever it is in a slice that has 8 bytes. That being said, we have been writing code for 1 hour. So we're going to take now the usual pause for hydration and stretch. Typically it's a stretch one, but with the heat that we have, I think the main concern is hydration. Nonetheless, we have the habit of calling it the stretch pause, and I'm going to once again take advantage that I have infinite channel points, and channel points redeems they should work. So let's try that again.
Prefect Dargan just redeemed Streech.
Okay, so what the TTS said, I am redeeming Streee. I will see you in a couple of minutes. Don't forget, everybody, to also hydrate and stretch. See ya. And we're back. So let's continue. We have greeting and end of file. I'm going to write the reference at the end. We're going to continue with the writing literal. Why is that? Because as we have already mentioned, the end of file symbol looks like literal length. So if literal is empty, which is the same as length 0, which is always invalid, or if the length is longer than it must length literal, we also bail. So now as for the conversion, we need to have an slice, which is the endian conversion of the literal length to, and we can choose if it is little endian or big endian. So problem is, okay, not to little endian or big endian, but little endian or big endian bytes, because as you can see, this gives us a byte array. It's a byte array in the slice. It has the exact size depending on the number of bytes of the data type. This actually creates kind of a problem. Because usize doesn't always have the same size. It can be 4 bytes or 8 bytes depending on the platform. So in big endian, right? So let's imagine that we have literal length is equal to 257. Okay, and that means we're using a 64 platform. Then that would translate into 00. So to the bytes, so the bytes would translate to 00, 2, 3, 4, 1, 2, 256, 257. Right? That would be this. U64 big endian. In little endian, it is just swapping out. Well, let me change this a little so we know what we're talking about. All right, something like this. So obviously B bytes works better for us because the bytes are basically in the same order probably that we want to have them. But we don't need all the bytes. So the other problem is again that this should work even when we're working with 32 bits architectures. So solve when get max literal equals to, let's say, 3. So we want the 3 last bytes, right? So they start at 8 minus 3, right? 0, 1, 2, 3, 4, 5. And here 4 minus 3 start at 1. So we start at bytes for number length minus self get max length literal. Now from there until the end. Okay, yes, I'm shadowing. Oh yes, and I cannot shadow because then here it goes out of scope. And length is bytes. All right, so what's the problem? Ah, yes, size is unknown, blah, 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 because it has to be important. Cool, cool, cool. So now in bytes for number, and we have all the bytes that we want except for the first one, because for the first one, we want to switch on the topmost bit, because that is the bit for marking that this is a literal break. Now, can we do that directly? So I'm thinking that if I change it in place, no, I thought it shouldn't work. And it may not work, it may be copying around the buffer again. That would be sad. I think it works. So obviously to actually write, in this case, we don't need the internal buffer. Only this. And then of course we can't forget that we actually need to write in the literal block. All right, and I think this implements write literal. So what about write reference? So let's start changing the edge cases. So minimum length is break even. While maximum length is max length reference. As for distance, again, this is not a problem. Distance 0 is the only that is wrong. And no, this is reference distance is too large. Okay, so now we have finished with all the assertions and the checks. So now, how do we write a reference? We need to write a length, but here's the thing. And this is why I'm not a good developer. This part is a function. This is a function that is actually write length self oh, and also we have a problem here because we were writing literal length directly, not through the codification. So in some cases it was run by one. So we'll codified length. Okay. And also we're going to add if is literal. Example. No, you know what? Directly literal mask UX. Why? Because then take this block from here to here. Oh yes, we cannot add it here because it's an implementation of a trait. See this in me. Yeah. So now the codified length is converted to be bytes, and then we extract the last bytes, and then we mask with literal mask. literal mask, symbol, flag, mask. All right. So now writing literal is just serve write length with a codified length, which is actually serve codify literal length of literal length with a mask of the mask for literal, and that's it. So another thing we can do is to get these two numbers into a constant. Symbol mask literal or f u8 equals s. Very lengthy name, but I think it is worth it. Separate it here, put it here. Oops, there is a typo. Cool. So now in order to write the reference, we need to call write length or serve codify reference length of the length that were provided. So don't forget this function, the codify functions are functions that we created back in the day in order to shift the numbers up and down with regards to the floors, right? The minimum values that are valid to encode. Cool. And obviously here we don't need a mask. And then how do we write the distance? Well, actually, writing the distance is the same as writing the length, but without adding the mask. Now, the reason why I created the function like this is in order to be able to manipulate this, right? Because if I just say write IU size with this number of bytes, we could, and I don't want. I see some problems with in mixing code. One of the things that I'm already removing is that I'm assuming that the distance is codified. Write distance is only used once, so we could actually write distance as a raw distance and call ourselves codify reference distance inside. But just in case I found an elegant way to merge these two into one, I'm going to do it like that. Oh, and yeah, I made a mistake. It's not, here we are removing bytes, so it's not get mass literal length we're removing. It's actually bytes for length. And here we need to remove bytes for distance. We don't need a mask for distances. And basically that's it. So very similar functions, and especially if we take this out, but we also need to consider the mask. Calculating this can be kind of tricky if we try to return the slice. It's not going to work, as you know. So I think this is actually a nice way to do it. So coming back to like reference, now we describe the distance, codify the distance or distance, and we don't need any other parameter. And there we have it. So we have now written this encoder. Let's change a little bit of the documentation. Fix summons. Right. And oriented implementation of encoder. This encoder writes all symbol as use all bytes. Lengths, including the symbol la, takes like, let's be syntactically correct. Lengths take an integer integral, a non-decimal, so it's an exact number of bytes to go. Distances also take next number of bytes to go. All right, so now the errors that we have here come from the tests. So now let's be real. New depends on, first we need a writer or something that implements a writer. Luckily for us, vectors actually implement a writer. So the writer can be just a unit of all UV equals vector of 8 new and a mutable pointer to this vector works for the writer. Then needs EOF. We're going to say true because we are, oh no, we are going to make it fail. So false. What else do we need? Bytes for length and byte for distance. In this case, it's going to be just 1. And here, we're going to have 1 with a true. Why is that? Because if we write EOF, the vector is going to be equal to EOF is encoded as a literal length. So as a length, bytes for length is equal to 1 single byte. And it is a 0 with a high bit set. It should be this. So as you can see now, this is another advantage of using the write trait instead of writing to a file, because it makes the tests quite more simple. This fails because it should be mutable. Yes. There we have it. All right, so now we have this test working. Now, write literal. So once again, we're going to create the vector. And we are going to create an encoder with 1. And this is important. This is an edge condition of empty literal, but then we will need to test what happens, what it is the different encoding when its COF is true or false. Right? In this case, it doesn't matter. With an empty literal, it should fail. And when we are trying to write a literal with the size, and this is going to be problematic. What's up? Yes, must be. This may fail because it can be calculated as a constant. All right. So this can happen a lot in tests, right? And this can happen a lot also in real life. So I think that what we did in the lost era is to create methods that class methods that calculate the max literal length given bytes for length. But I don't like it. So instead of that, we are going to create another metadata. Okay, we're going to how was function that we used in new here, resize, via resize. Resize, the size being this, and the value is 0. Work. So now, if we want to write this as an error, and if we want to do this with 1 byte less, this should work. And not only should work, we should know what's what's the first byte of the output. It should be offset. Right, then we're going to clear the vector, create a new test. Yes, we're going to create a new test. Same as before, but now we don't need end of file. And that means that now this test should succeed. Because now because we don't need to reserve space for end of file, we have one more maximum in the maximum literal length. While it is still encoded with all with all bits set. All right. So now we clear E, we create an encoder. We're going to test this 1, 2, 3. So we're going to write the literal that. And now what happens is that the result of the vector should be equal to we have end of file, so we need to add a +1. Sorry, we don't add or remove from the size, so we need to have a 3, the height bit set, and then on 8 2 1 2. Okay, that test should work. The tests are quite long, so I'm going to make a run for it. Now it's going to fail because I don't have a lifetime specifier. For the writer. And yes, I also need to do it here. And then line 71. Cannot assign 2 bytes for number which is behind an AND reference. That is perfect. Perfect. And obviously we have immutable borrows because of course we need to have some immutable. Let nice size. Perfect. So now this builds. And we have some tests failing, which is absolutely perfect because that's what we want to fail during tests, not in production. So it's in line 199. This. It says that left is 192. So we have a maximum valid length. The maximum valid length should be encoded Let's take a look at it. So remember, now this block, so what we're trying to test here is writing a literal block that has a size of get max length literal into a literal. So now I write literal. This literal has a get max length literal size. It is not larger, it is exactly this number. So the first thing that we are doing is to codify that literal length. And what we're doing is, once again, we're having an assert that that row length is smaller or equal to get max length literal. Once again, get max length literal. It is exactly the same. And then we're calculating where we're taking that length and we are removing it by the literal length floor. In the literal length floor, which in this case is true, so the literal length floor should be 0. So it should be maximum literal length minus 0. So what is the maximum? The maximum length literal is 1 to this. Oh, maybe there is a parenthesis problem. Let's try this, because if that's the problem, we also need to change it here. Yeah, all right. Operator precedent. Problems? All right. Good, good, good. Because tell to change that. So much so that now that I'm thinking about it, we can make an internal function, which is a get limit. And that receives the number of bits, which shouldn't be a new size, but because I'm using new sizes all around. U32, which is the actual type that is used for 4-bit shifts, and the floor. And this returns this. So now get map reference length is actually the same as self get limit of this, and the floor is this, and the floor is that. Obviously this fails because it's not a U32. Right, much cleaner. here, Siri, let's hope that the compiler knows how to optimize this. And this is of course. So as you can see, when I get a little bit tired, I forgot how to write things properly. I should have started with this function and then going down. But yes, old habits die hard. And in fact, something similar happens here. This codifies the arrow, basically the same function. Right, we have a floor, we have a ceiling, and we reduce the number we codify by having the floor except here. And we have a fixed one, and here we have a variable floor. So you know what? We're going to get the functions like that because of that reason. Anyway, so we have tested this. Let's try to write a test for write reference. So let's try also the same with this. And now we start with the edge cases. Get break-even length. Oh, it's not stuff. So I'm going to try that writing references with the lengths between 0 and break-even fail, and that if we write one with that plus one is an error. For the break-even length itself, is okay. And for the maximum length, why are we creating another encoder? Yeah, I don't see the point. Let's reference one. It's okay. So let's continue. Edge condition test. Distance now are too small. or too large. And the edge conditions when it works. There are two actually, but one has already been tested. Is that with a distance of 1 it works? Yes. No. Oh, okay. Okay. So now, yes, we're going to create a new encoder. Do we need to create a new encoder? No, the encoder is stateless except for the vector. The only thing we need to do is here's the vector. Okay. So I'm going to this. Now, the distances here are coded to be 2. That's yeah, because there are distances. Distances are starting from 1 until whatever. So now the result has to be equal to get break-even length, that is encoded as a 0. The distance is 2, but we need to remove 1 because when we codify distances, we remove 1, we subtract 1, sorry. So it is C1, and then these are the two values with a plus 2. It's going to be CO2, CO3. All right. Okay. Okay. Anyways, let's have all of this, and everything passes. Correct. So now there is another test that I want to do that I didn't do for the literals, but I think they're easy to do for references, which are impedance tests. So now we're going to have both the lengths and distances to have 2 bytes each. We're going to write exactly the same, but now the results are different. First, the get break-even length is encoded in 2 bytes, so 0, 0. Then the distance is also encoded in 2 bytes, and because theoretically we're using big endian, it should be this. And as you can follow, basically we're just adding 0 bytes in the middle. Perfect. So we also have the endianness correct. And with that, we have our fixed byte converter, our fixed byte coder. Sorry. So it has its documentation, it has its tests, and yes, fix right fix as to equal sign up meet. All right, and basically that solved the issue at hand. But now that we're here, let's rewrite our compressor, shall we? So in our compressor, instead of using the mock encoder, we're going to use the fixed byte encoder. So obviously, we don't need an encoder config or symbol. Second, so the first thing that we need is obviously our quote-unquote vector, right? Our implementation of a writer. Instead of that, we're going to use directly stdout. Now, this is not the best idea to do it like that, because I don't have it locked. I think that if we lock it, the writes are buffered. I'm not sure about that at all. Just in case, we're going to do it because we're also locking, if I remember correctly, we're also locking, oh no, we were not locking the input. Yeah, the input doesn't need to be locked. We don't need to be buffered. So now for our encoder, what do we need? We other new expected for, yes, give me those, the writer. So stdout handle. And then needs EOF. Going to assume true. and then bytes for length and bytes for distance. And I'm going to use a bytes for length of 1, meaning that the maximum match that we can have is around 127 plus the minimum, so 128, 129 bytes. But for byte for distance, I'm going to use 2, meaning that we're going to have a sliding window of around 64 kilobytes. I think that makes a good solution. So now, if we think about it, and that is the beauty of the design that we have started, we have the compressor now writing to standard output. So we read the standard input, we compress, we flash, and we're done, right? We don't need to write anything of this because that is for the test. We may create another example for that. I think we should for the optimization of the encoder. But that's a story for another day. So now in theory, if you do cargo now, this sample compress from from the README to your test output. It run, and the test output is smaller than README. Not by much, but I think that is because this file is again is too small. Basically, the majority of the matches have a distance of 1 byte. If instead of that we use the license file, now we see a much higher difference, right? So that's a problem with a fixed size encoder. It doesn't matter if it's the byte-oriented one, which is this one, or a bit-oriented one, which is the one that we implemented in the Nostera. It leaves a lot of gaps. So, because this is actually a real compress, I'm going to move this to a new example. I'm going to call that encoder. Yeah. So in this one, we're going to keep the damping of the symbols because that's what we want to do. But obviously, the problem is that I removed some code that was actually useful. However, we actually have that code. Thanks to git-diff. And now we'll say issue. This one side. And I use. All right. All right. So basically, instead of that, I'm going to do a trick. Right. So bear with me. We're going to move the new compress out of the project. I'm going to remove the encoder dump. And I'm going to do a git move of example compress to example folder dump. Oh, yes, because I have removed the original one. So I'm going to discard the changes compressed. And now I'm going to move it. So encoder dump appears as move the old compressed, now called encoder dump. And we move back the compressed into examples. And there we have it. Now we have a compressor that is now, remember guys, today at this time, we have a compressor that acts like the simple version of gzip. It can compress from the input, standard input to the standard output, and it actually compresses. For certain values of compress, we are doing what we can with the tests. We're lacking the compressor, of course. But with using the eternal words of a chess player, it just works. Okay. So now we're going to commit feature working compressor, and this moves in the example compressor to one example 5, and this 8 is the compressor example that moves from std in std cd equal to std. Signing off, commit. Right, so that's actually the goal of the card, right? Writing a compressor that works. So what's the next step? The next step is obviously to write the decompressor. In order to write the decompressor, we're going to write, we need to write the decoder. I have not checked the code from the Lost Era. I think that we wrote the decoder first, and then the decompressor. So I'm not going to create a pull request for this, merge, create a new card. So I will do the pull request, merge, etc. of a stream. I will take a look at the Lostera code and think what is the next card, which I foresee is going to be writing the decoder. And that would be our next honest stream, right? The whatever new card we have, probably the decoder. I will not be streaming tomorrow. So I will see you all in a couple of days. For those watching the VODs in YouTube or here in Twitch while it lasts, thank you also for watching, even if you couldn't join us in the live. Thank you, everybody. This has been the Perfect Argent, signing off.